That's big enough you can see it, I'm pretty sure. All right, so I picked out and highlighted some ones that I want to be sure and hit. But first, before we do that, are there any of these problems that you ran across that are giving you trouble and we need to deal with them? So we don't run out of time and then leave you hanging. Moles conversion. Okay, we're going to hit a few of them, unless you have one in particular that you'd like to go to. Do you have? You don't have an? Okay. So we should cover those unit conversions. Anybody else? Or is that giving everybody trouble? Okay. All right. So let's see. These problems, when we get to chapter 4 review, they start renumbering. So that's why I put chapter 3 up there. All right, we're going to do the first one. And this is an exercise in determining, well, in our discussion of average atomic mass, you understand that it's a weighted average. Depends on the abundance of each isotope. We're going to use those concepts to determine what is the natural abundance of the copper 63 isotope. Okay, and in order to do that, we've got to use a little algebra. Right? Everybody had algebra. Remember, let X equal something and then off to the races. Yeah. Okay. So we've got, let's see, I'll put it up here. 63. And write it that way. 63 copper has what type of abundance? Oh, we don't know that yet. That's the question. So it has X % abundance. So that means, since these are the only two isotopes that they're telling us are go into the calculation of the average atomic mass, then 65 abundance should be 1 minus X, right? And let's make X a decimal equivalent of percent. I think it's, because if this is the abundance of this one, then what's left over? They have to add up. If they're percentage, they have to add up to 100. And if they're fractional, they have to add up to 1. So that's why I'm using 1, because X is going to be fractional. Okay. It's easier to do the math that way. Okay, so now that we know that if we, and they didn't give us, or did they give us? No, they didn't give us exact masses for each of these isotopes. You know that they're not equal to 63. The only one that's exact number is copper 12. I mean, it's 12 infinite zeros. So the rest of them are going to be fractional, but they didn't give that to us. So we have to use these values as if they were the true values. And if we take the fractional abundance of that isotope, the contribution that it makes is going to be X or 63 times X. That's its contribution. The fractional amount of 63 will give us the contribution to the final amount. And 65 times 1 minus X will give us the contribution of this isotope to the total. Okay, and you just add those together. So what we get is, added those together is equal to that value, 6355. Atomic mass units. So now we have an equation in one unknown. We just have to solve for the X. And that'll give us the fractional abundance of 63. So let's see. If we bring it down here, 63X, and this is plus 65 minus 65, X equals 63.55. And now what we want to do is get all the X's on one side and all the numbers on the other side. So if we leave the x's over here, that's a minus 2x, correct? 63 minus 65. And then this 65 comes over here as a minus. And that's 5 for 1.45. Yeah, 1.45 plus this gives us 65, but that's a negative because when that comes over here, it changes sign. So we've got negatives on both sides, which is all right because now if we solve for x, the negative divided by negative is positive. So x equals 1.45 divided by 2, which is what? 0.7.
Was it divided by -2? Negative.
Yeah, they're both negative.
Okay.
Yeah. Let's see, is that right? 2 divided into 1.45, that's 0.7. 725. Or since we only have 2 significant figures, maybe 7.73. Well, then we have to pick the best answer from the available ones. And the closest one is 70%. Yeah. Okay. Yeah.
Okay. So the 65 turned into a fraction.
Oh, well, what happened was we kept the x's on this side. So 63 minus 65 is 2.
Okay.
And then we took this one and brought it over on this side. And it became that.
As far as the 1 minus x in the beginning, like next to the 65 and minus x, is that just something that you have to memorize?
This one?
65. No, whenever you wrote the values initially.
This one?
No, the first thing.
Oh, this one?
Yeah, 65.
Now that came from here,
But where does the 1 minus x?
from the relative abundance.
Is that just something that you have to just memorize those ones?
No, we logically assumed it. We let x equal the percentage or the fractional amount of 63. So the total of that fraction should be 1.
Okay.
Add them together as a whole. Or if we express it as percent, right? If this were 70%, that would be 30%. Because it'd be 100 minus 70.
Okay.
But I use the fractional equivalent. So this would be 0.7, and that would be 1 minus 0.7, be 0.3. Yeah. All right, that's 1. Uh-oh. Did I erase something you needed? Okay. All right. 3. This is kind of a trick question, just to see if you paid attention in class. The average mass of carbon atom is 12.011. That's the value you're going to find on the periodic table. Assuming you were able to pick up only 1 carbon atom, the chances that you would randomly get one with a mass of 12.011 is what? 0. Yeah, it's an average. Right? No carbon atom is 12.011. Right? The carbon 12 isotope is 12.0000, and then the 13 is 13.0 something, I forget. And 14 is also a fractional. So you're not going to find one that's 12.011. That's a weighted average. Okay. Are we coming to one that was it giving you trouble? 4. Let's see. What's the mass of 4 atoms of copper? 4 atoms of copper. Well, the bridge between numbers of atoms, molecules, ions, and mass is molar mass, right? Grams per mole. That's the way you go from weight or mass to numbers. You've got to know moles before we can change atoms to grams. The question is how many grams is that way? So we got to convert this to moles first. right? And that's Avogadro's number. Right, okay, so that gets rid of atoms. Now we got moles. Now we can change moles to grams. Right. What we need is, what's the molar mass of copper? Now that we've got it in moles, how much does a mole of copper weigh? Well, I've got to look at the periodic table. And let's see if I can get that shine off of it. 6355. With 63.55 grams per 1 mole. Moles have already canceled, atoms have already canceled, and we're left with grams. That's what we want. So we just have to multiply that out. Multiply and divide. Right. 4 in the numerator times 63.55, and then divide by Avogadro's number. And I get 4. This is a counting number, right? Like 9 pencils, right? So it has infinite significant figures. We can keep as many decimals as we want. I'll round it off to 2 times 10 to the minus 22 grams. Because we ended up with grams over here, our answer is going to be in grams. And that would be E. Does that make sense? This is dimensional analysis. We get from where we are to where we're going by conversion factors. Right? Each conversion factor is equal to 1. 1 mole is equal to that many atoms. 1 gram is equal to that many moles. This is still not clicking. Well, this was a chain conversion. We had to decide how are we going to get numbers to mass, right? The only bridge we've got from numbers to mass is molar mass. So that dictated conversion of atoms to moles. Once we got moles of copper, then we have a conversion factor for moles to grams. This is where we are. This is where we want to go.
I get the rest of it. Like, I just don't understand how to break down the atoms to the moles. Like, is it just each one? Like, is it like 1 mole equals 1 atom? Like,
No, 1 mole equals 6 times 10 to the 23rd atoms.
that's all the other numbers.
Yeah. It could be. I think you're stuck on just the concept of only 4 atoms. How can only 4 atoms be blah, blah, blah? It's, if you set this aside in your mind as not a physical problem, but a math problem, all we're trying to do is convert units. So we're converting units of X into Y and then into Z. We could substitute anything in here and the math would still be the same. Right? We could say, I don't know, 4 cubes.
Okay.
4 cubes of anything, and then convert our cubes into some other unit, and then we have a conversion from this unit to that unit, and it's pure math. Dimensional analysis, you can use it in any science, not just chemistry. I think that's where you're stuck.
The 63 number is just the copper's mass.
Yeah, it's molar mass for copper.
Okay, that's wrong.
Yeah.
Yeah.
Yeah, once you find out, right, when we got rid of atoms and left us with moles, and then in order to go to from moles to grams.
So the grams, right, you have to find the mass of the element on the grams, right? So
That's a mass per mole. Yes. Okay. And you can't use this unless these units are in moles.
Okay. But
we're still numbers. Okay. Going from numbers to mass is molar mass.
But the mass of an atom is always grams per mole, right? That's the unit of it, grams per mole.
The molar mass.
Right, is grams per mole.
Yes. If you want to use that chart and read those numbers off there, it's grams per mole. Yep. All right. Number 6. I think we're going to run out of time. Unless I skip some of them. That means we won't have time for a lab today. I wonder if we could do a lab on a different day. Let's review. Next week is the exam, plus we're getting into new material, right? So we can't have a lab on that day. Let's see. Oh, wait a minute. Yeah, all right, that's right. This is lab techniques today. I was looking to see if I built in any. No, all the times are taken up when we need to do labs. So either we do the lab today or we don't. That's the only choice. 6. All right, you have a sample of zinc and a sample of aluminum. Zinc and aluminum. Okay. Those two samples. You have an equal number of atoms of each one. So let's say, just for argument's sake, let's say we have a mole of each one. Each one, we got a mole of each. Okay. Which of the following statements concerning the masses of the sample is true? The mass of zinc is more than twice as great as the mass of aluminum. All right. If we have a mole of each one, it's easy to find out what the mass is, right? Zinc would be periodic table. Don't have to be squinting at that one.
Zinc is 65.4.
6539, rounded off.
I'm gonna say 65.38.
38 something. No, just 38.
What y'all? 65.38.
It's going to work either way. We'll use your number. 65.38. And that's that many grams for one mole. How about aluminum? It's 23 something, isn't it?
Yeah.
No, 26.
26.98.
26.98. Okay, we agree on that one. 26.98 grams. Okay, how about that first statement? The mass of the zinc sample is more than twice as great as the mass of the aluminum sample.
True.
Yeah, because 2 times 26, well, 2 times 27 is 54. That's more than twice. They're same numbers because we picked one mole of each one. Right. So A is true. I guess we found our answer. Right. During a test, if you found your answer, move on. Found the right answer, I should say. Right. Some of these multiple choice questions are tricky. Right. They take the mistakes that lots of students make and they create an answer from that mistake and make that one of the selections. So if you make the same mistake,
Sorry.
that's okay. Do you have some drops or something for it?
No, not yet. I
Oh,
went to CBS Docs and be like, so I just.
oh, okay. Okay.
I'm okay.
All right, 7. A sample of ammonia. Now, in this problem, in a subsequent problem, I did say what ammonia is, but here I'll tell you, if you see ammonia on an exam, on this exam, you need to know what it is. And ammonia is NH3. Has a mass of 43.5 grams. So the actual mass of that sample is 43.5 grams. How many molecules are in the sample? Okay, this is like one of those that was giving you trouble, correct? Conversions. Okay, 43.5 grams. Well, we've got to go from mass to numbers. And the only way to get there is molar mass. cancel the grams, and leave us with moles. So what's the molar mass of ammonia? Well, it's 14.01 is,
How did you get that?
it's in the problem.
Can't say really well.
Oh, okay. Okay, you're forgiven. So 14.01 for nitrogen, and then hydrogen's 1.01 times 3. So that's 407, 1704. All right, that converts grams to moles, but they want to know how many molecules. So what's the magic number? Right. Avogadro's number times 10 to the 23rd. There we go. And that gets rid of moles and leaves us with the answer we want, molecules.
So you break down the ammonia,
Yeah, this is grams per mole.
so we got 14.01
That's nitrogen,
nitrogen.
and this is 3 hydrogens.
Okay,
Right, just from the formula.
that's 17.04.
Correct. So divide that into this times that value, you should get 2.36 times 10 to the 23rd. In the interest of time, I'm not going to calculate that one. We'll go to the next one. Which is number 8. How many moles of hydrogen sulfide are contained in a 49.7 gram sample of this gas? All right, in this one, you've got to be able to write the formula of hydrogen sulfide. Okay, do you remember what that is? It's got hydrogen and sulfur in it, correct? Sulfide is a chalcogen. All right, it's an oxygen group, so it has a -2 charge. Hydrogen most often is a +1 charge. So you need 2 of these. So H2S is hydrogen sulfide. Okay. We're starting off with 49.7 gram sample. And we want to convert it to moles. Right. So we need what's of H2S. Right. Well, 2.02 for the hydrogens. How about the sulfur? Sulfur is
32.06.
yes.
Oh, 0.7.
Can't take it back. It's already said. So 3408 is the molar mass for that molecule, for that compound. Right, and that'll tell us how many moles. Yeah, that tells us how many moles of the compound. All right. But they want to know, the question is, how many moles of, oh no, that's right, hydrogen sulfide. Okay, I thought they were, never mind. I thought they were looking at how many moles of one of the elements. So we don't have to do that. And that should be 1.46 moles. Let's see if that's reasonable. Yeah, 34 into 49. Yeah, that looks reasonable. All right. 10.
People one mile over the 34.08 grams. What was the second step?
That was it.
It-
Yeah, I misread it. I thought it was asking for how many hydrogen atoms or how many moles of hydrogen, but it didn't. So I stopped there.
Mhm.
We got another one coming up where we do that. So For which compound does 0.256 mole weigh 12.8 grams? So what's the molar mass? I abbreviate molecular weight. Is mass per unit moles. And the mass we've got is 12.8 grams, right? And the moles is 0.256. I will have to calculate this one in order to make the comparison. So 12.8 and 0.256 divided equals 50. 50.0 grams per mole. Remember when you do a calculation, you have to do the same thing to the units that you do to the numbers. If you divide this number by that number, you have to divide this unit by that unit. That's why the units of measure are grams per mole. Okay. All right. So now we need to compare that with A, B, C, D. Is there an E? E is none of these. Okay, so we'll have to see if it's none. What are our choices? C2H4, C2H4O, CO2, carbon dioxide, CH3, Cl methyl chloride, and C2H6. So we have to calculate the molar mass of each one and compare it to that one. Okay. So this is 2 times 12.01 is 24.02, right? 2 times 12.01. Okay. And 4 hydrogens, 4.04. How about 1 oxygen?
60.
Yeah. All right. So that's 6, 0. That's 14. Carry the 1. That's 44. So that's not it. How about CO2? That's 12.01 and 2 oxygens. So that's 1, 0, 4, 4, 4, 4. That's not it. How about methyl chloride? 12.01 hydrogens and chloride. I got it memorized. That's all right. 3545. That's in the periodic table. Okay, that's 8, 9, 4. Let's see, 8, 10, 4, 5. That's it. That's the closest one. And we can do the others, right? What's this one? 24.02 for that carbon. 2 carbons. And then 6.06. All right, so that's only 30. Right, so we found it. It's this one right here. Methyl chloride. Some of them take a little more work than others. But it's not something we can just look at the problem and get the answers. I mean, it doesn't just pop into your head. 11. Okay, calculate the molar mass of barium sulfite. So to do that, you got to know how to write the compound. We know it's got barium in it, correct? What's sulfite? It's a polyatomic ion, correct? Sulfite. Sulfite. Yeah, S.
I was saying.
No, you were saying C.
Say it in my head. I think I said. Oh, let's see. I saw it.
CO3 is carbonate. Okay. So what's the charge on SO3?
-2.
Okay. How about barium? Let's see, where's it located? It's an alkaline earth, right? So what's its charge? +2, always. So that means that's it. That's right. 2 to 2. So what's barium? Molar mass of barium. 137.33.
37. There you go.
Okay. Sulfur. We did sulfur before, didn't we? So 30.
32.06. 07.
And 3 oxygens. What's 3 times 16?
48.
Yeah, there you go. We add that together. That's either carry your 1 or and 17 carry your 1. And let's see, 4, 8, 11, carry your 1, 2, 17, 40. Is that on there? Yeah, E. All right, 13. Now I just thought just occurred to me. If we skip this lab, the next lab, the next lab will be in 2 weeks. It'll be Boyle's Law. Gases. And that's the first one where you have to, it's a formal lab. So your notebook has to be set up and ready to rock and roll.
Well, we have a paper.
Yeah,
If he just scrolls through and just shows us that we actually work one out.
Yeah.
No.
Okay. So what we could do, I mean, you won't have the hands-on experience, but what I can do is make the video available, the demonstration. It may already be in there for the lab, yeah. And then use that to fill out the lab report, yeah. Because this is an informal report. You just fill this out, turn it in. Okay.
So for the formal report, we have to do we need to figure out how to do
I gave you an example
Okay.
of how to write one.
Okay, because I was wondering about how to do the pre-lab questions again, so just use the example that you gave.
Yeah. Right. When you set up your notebook for the next time we come in, which won't be next week because next week's an exam, the week after that, then you need to set up you have your table of contents. Right?
Yeah.
I haven't done a check on your notebooks yet.
Well, yeah, I think.
Do you have them with you?
Yeah,
I thought it said next week.
we haven't done it yet.
Okay. So when you
Number.
right, when you set up your notebook, you need your name on the cover, your name, the course, which would be CH213, and then the semester, fall 23. Right, that's a minimum.
Right.
You can put anything else you want, but you got to have that. And then on the pages, you open your book up. Right, here's the divide. Open it up, and this is like the backing for the right. This is not a page.
Right.
First page is number 1. So you flip that, and now you're on. Now you flipped it. This one's going to be 2, and this one's going to be 3.
I did like 100. It's
Yeah. So if you're going through and you're numbering it, and you end up with an even number on this side, sometime stop. Right, you did something wrong. Go back and find out where you messed up. So how do we do a correction? You're doing it in ink. So if you make a mistake, you just cross through it and write the correction. And technically speaking, if you make a correction, say you put a 4 here and it should be a 3. Right? Cross that out, 3. You should initial it. Any correction should be initialed. Okay. And you only write on this side. Leave that blank. The left-hand side blank. That's for overflow and big mistakes. Okay, so once you get that done, that's what I want for the first notebook check. But we're probably going to have to do both at the same time, unless you bring it next week. Right, then I can do this one independent of the one for Boyle's Law.
I have my
Huh?
I have my
Do you have it set up this way?
Yeah.
Oh, okay. I'll check it before you leave.
If you don't have it.
So when you set up for Boyle's Law, which is going to be a formal lab, into this is going to be your first page. You could do it on page 1 if you want, or page 3, doesn't matter. Table of contents. You got that in there? Okay. Now when you start putting experiments into it, you put the title and then you put the page number that it starts on. That's it. And then you go to that page number and you start with, you give it the title. Then you give it a introduction. You know, why are you doing the lab? What's it all about? Just in a few words. Then you do a safety blurb. What do you need to be careful with? Okay. Then you do materials. Right. What are you going to need to do the lab? Now, sometimes the labs have those materials in a separate table. Sometimes they don't. You might have to dig through the lab, find out the stuff that you're going to need and write it in there. And then you do the procedure. Right? Step 1, step 2, step 3. Do this, do this, do this, do this. And then you can put your pre-lab questions anywhere you want. Right? So pre-labs could go here, they could go someplace else, it doesn't matter. But the pre-labs are the ones before the lab. You have the answers written in. This is stuff, this is stuff, this is stuff, this is stuff. That has to be prose written in. When you get to data, you're just reserving space for data.
We got a whole page for that.
You got plenty of pages. The whole page would be fine. But what I suggest is when you know what type of data that you're going to get, like if you're going to have a whole list of the stuff and you know what's going into it, like for the Boyle's law, you're going to be measuring volume at different pressures. Right? So you set up a table and just make enough room. Right? So to put all those values in there, there'll probably be 10 or 12 of them. That'll be your data. And then on the next page, and we're still writing on the right-hand side only. The next page, you're going to put in calculations. And for that, you may have calculations from the pre-lab, right? So you'll put those in there already, but you'll have space left over for doing calculations that the method calls for this. And you don't have to do all of them here. The calculations is just to show if you've got multiple calculations of exactly the same type, just put one of them in. Then once you get the calculations done, you're going to have, let's see, post-lab questions. Of course, you don't do those until you finish the lab. Sometimes the post-lab questions refer to data and other calculations and summary and conclusions. In the summary and conclusions, you want to summarize what was done in the lab in just a small blurb. And then you want to say, what does it mean? And that's why I gave you a copy of the rubric that I used to grade it. It shows you what I'm looking for, right? And you want to have circle things all the way down the left-hand side. That's the highest point you can get. And you can look at the right-hand side and see, right, you don't want to go there. I think I also gave you a handout of common errors that are made. Yeah. So pay attention to that. And that'll show you, where students in the past have lost massive points by making these errors. That's it. You'll have, for this stuff here, you're going to have space reserved for it. That's all you have to do when I check your notebook for that lab. That's what I'll do. I'll check your notebook before we even start the lab. Okay. All right. Oh, I didn't mention one thing. If you want to draw a graph, put it on the left-hand side. Right. If you want to produce a graph with your data in, say, Excel, then you can print it out and cut it and paste it in your notebook. But if you paste it in a page, so this is a page, and you got a graph here like that, like that. If you paste it in there, then sign or initial it.
So stuff like this will we be doing together, like in class?
No, you do this on,
Won't do any of the other
you
So
do that on your own.
all our formal labs go in the lab notebook, right?
Yes,
Okay, and all the informal labs, we don't have to do anything in the lab
No.
notebook? Okay, that's fine.
that's voluntary. If you want to just to practice, you can, but you don't have to. Only the formal labs go in your lab notebook. Mandatory. So you sign across the border, right, where you pasted it in. That way, if the glue hardens and it falls out or somebody rips it out, you'll know something's missing. You may not be able to recover it, but at least you'll know. Okay. Let's see, where were we? Did we do what? Yeah, 13. What's the mass of 6.761 mole sample? 6.761 mole sample of sodium hydroxide. So you got to be able to write sodium hydroxide. All right, what's sodium? Na. What's hydroxide? It's a polyatomic. I'll give you a hint.
I was trying to find it, but I can't.
OH minus, this is a plus, so just 1 and 1. Okay. So if we're going to convert that to mass, we need what? Moles on the bottom, grams on the top, right? Whenever you see that relationship, molar mass. So sodium is what? Molar mass of sodium is 23.00. Rounded off. Oxygen and hydrogen. That's 1, 0 there. Let's see, 10, 30, 40. Forgot to carry my 1. 40.01. So if we multiply that out right, it should be 270.4. Let's see, does that make sense? 6 times 40 is 240, and then there's another 3/4. That's, yeah, reasonable. I was just doing a quick head calculation. Okay. All right, that was 13, 15 coming up. Yes, 270.4. 15. 1 molecule of a compound weighs 2.93 times 10 to the minus 22nd grams. 2.93 times 10 to the minus 22nd grams per molecule, right? 1 molecule. That's given. The molar mass of this compound is what? Well, what are the units for molar mass? Grams per mole, right? So we leave grams alone. But we need to get rid of the molecule. And leave us with moles. So what's the relationship there? 2 and 23. All right. So that gets rid of the molecule and leaves us with grams per mole. That's what we want. Is that one messing with your head too? Okay, so that should be 176 grams per mole if we do our calculations right. Right. 17. The ones we're doing now.
Yeah.
Well, let me throw 17 at you and see if how that affects you. A compound is composed of element X and hydrogen. So it's got probably like that. It's got those 2 elements in it. Analysis shows the compound to be 80% by mass X. So it's 80% mass of X. So how much hydrogen is there?
Why is it nice?
It's grams per 100 grams of sample. Grams of X per 100 grams of sample. That's what percent means. Parts per 100. See, percent is one of those things that if you don't know its origin, it doesn't give you that information. Parts per 100, it could be grams per 100 milliliters. It could be milliliters per milliliters. You know, sky's the limit. So when they tell us mass, now I know what it is. 80 grams per 100 gram sample. So how much of it is hydrogen? It's not a trick question. Yeah, 20%. Hydrogen. Because it has to add up to 100%. Right? If it's not 100%, then you made a mistake somewhere. 100% is the total sample.
Right. Oh, okay. Gotcha.
Okay, so that's what's given so far. Analysis shows the compound to be 80%. Okay, with 3 times as many hydrogen atoms as X atoms. So it's got 3 times the hydrogens per X. So the ratio is 3 of these for every one of those. Okay. Which element is X? All right. So if we're going to get at which element is X, we got 2 choices. If we know the atomic number, right, the number of protons, simple. But we don't. And I don't see any way we can get it from this. But we could also go for molar mass, because molar mass is fairly distinctive for each element too. So that's what we got to go for. What's the molar mass of X? We need grams per mole. All right. So we're going to have to make some assumptions here. Right? If this sample is, say we start off with 100 grams. Right? If we start with a 100-gram sample, that means we have 80 grams of X and 20 grams of hydrogen. Okay. If we have 20 grams of hydrogen, then we can find out how many moles of hydrogen that is. Because we know that the relationship here is like that, 1.01. So 1.01 divided into 20 is 1.98. 1.98 moles of hydrogen in 100 grams. We were also told the ratio. Okay? So 1.98 moles of hydrogen, we can convert that to moles of X. Right? This will cancel the moles of hydrogen and leave us with moles of X. Okay? We're talking math again, dimensional analysis. Right? So what's the ratio here? Right? For every 1 X, you got 3 hydrogens, correct? Okay. So now if we divide 3 into 1.98, that gives us, oops, 1.9. Did I do that right?
I really don't understand what you're
No,
I don't think you did.
that's not right. 19.8. There you go. Now we divide 3 into it.
I don't understand.
Okay. What don't you understand?
Like after you go to 19.8, why did you go on and do the 1 mole?
Okay. We're looking for molar mass of X. That's how we're going to find out what X is. Right? So the molar mass of X is equal to mass per moles. Right? So
there's
we know
that there's 1 mole of X and there's 3 moles of hydrogen. That was your meaning by that?
that's part of it. Okay. We need the mass too. we're basing our whole calculation here upon a 100-gram sample. And that means 80 grams of it is X. So we have 80 grams here. Right, that, how many moles of X does this 100-gram sample represent? So we have to get at it by going through hydrogen because we don't know what X is. So we find out how many moles of hydrogen are in that sample in these 20 grams of hydrogen. And now the ratio between X and hydrogen gets us how many moles of X. Because we were told the ratio is 1 mole of X, 3 moles of hydrogen. That cancels this one and leaves us with that one. So that's 19.8, right? Moles. Grams for that many moles. Oh, excuse me. No, it's not. I'm about to make another boo-boo. What's 3 in a 19.8? 6.6? Yeah. 6.6. There we go. Now we can divide that into 80. 12.12. Okay. What's the closest one to that in the periodic table? It's not exact. Yeah. There's a lot of experimental error here. It's like, what, 10%? Yeah, carbon. B, carbon. That's carbon. Carbon. Thanks. Okay. All right. Moving on. Learning chemistry is a process of being introduced to the topics, trying to wrap your head around them. You really don't understand chemical concepts until you work problems, and lots of them, unfortunately. 18. Which compound contains the highest percent by mass of hydrogen? Okay. A, B, C, D, and E. This is HF. This is H2S. H2SO4. H2O. And HCl. Okay. Percent by mass of hydrogen. So remember how we calculate that? We use the formula and assume we have 1 mole. So how much does 1 mole represent for hydrogen here? Well, it's 1.01 divided by 1.01 plus 3545 for the chlorine. Right, that's the total for 1 mole of that compound. This is how much hydrogen is in it, and the ratio is mass ratio times 100, because we're saying percent. Right? So if we say 1.01 and 3545, add that together and divide, and then 100 times it. That's 2.77%. And we just do the same type of calculation for the rest of them. This one's got 2 hydrogens in it, right? So the numerator for this one should be 2.02. But the denominator will have 2.02 plus oxygen. Right. So now we need 2.02, then add 16 to that, and divide them times 100. I get 11.2%. And this is percent hydrogen. Okay, H2SO4. So this one also has 2.02 in the numerator. And 2.02 plus sulfur. Was that 32? 3206. Or was it 07? Sulfur.
What was I saying?
3207 plus 4 times 16. 64. times 100. Okay. 2.02 here. And I'm going to add 3207.07 and then 64 and divide. And then 100 times that. That's 2.06%.
Did you do 4 times 16 because you were talking about?
Yeah, 4 times 16. Each, right. This whole molecule has 16, 4 oxygens in it. So a mole of the compound actually has 4 moles of oxygen. That's why we multiply by 4. And I should do this because I don't want 100 times that. I want 100 times the whole quotient. Yeah.
Okay.
Okay, this one's going to have 2.02 because there are 2 hydrogens. And then 2.02 plus sulfur, which is 32.07 times 100. Okay, 2.02, 32.07 plus that, and then divide it into hydrogens times 100. 5.93. 5.93%. And then HF. This is only 1 hydrogen, 1.01. And then 1.01 plus 19 for the fluorine times 100. I just rounded it off. And divide and 100 times that. And I get 5.05%. Right? So the greatest percent by mass of hydrogen is water. B. It was 18. Still copying this one? Okay. $19. A substance contains 35 grams of nitrogen, 5.05 grams of hydrogen, 60 grams of oxygen. How many grams of hydrogen are there in a 153-gram sample of this substance? This is a similar type of problem to 18, only with this one, we're not given the formula. Right? We're just given the actual mass of each of the elements in the compound. Right? So we're after grams of hydrogen. Right? So we have hydrogen is 5.05 grams. 5.05 grams. Plus the other stuff, 35 grams of nitrogen and 60 grams of oxygen. Right. Now, you can use percent, right? You can calculate percent if you want, but fractions work better. So I'm going to leave it like that. And this is the decimal fraction amount of hydrogen in that sample. Let's see, 5.05. Now we'll put that in the denominator also with 35 grams of nitrogen and 60 grams of oxygen. And then divide. So I get 5.05 times 10 to the minus 2. 5.05 times 10 to the minus 2 is, actually this is saying grams of hydrogen per gram of sample, because we didn't multiply it by 100. Okay, that's a fractional equivalent of percent. If we multiply that times 100, well, it'll be 10 squared times this would knock that out and it'd be 5.05%. Right? of sample.
So you don't add this up, you don't divide?
I did,
Okay.
I think.
So if you do 5.05.
You got them.
Hold on a second, let me do it again. 5.5, yeah, I could have made a mistake. 35 plus 60 plus, did I get those right? 35 and 60, yeah. And then divide. Well, yeah, 5.05 rounded off 2 decimal places. This total is pretty close to 100. That's why it looks that way. That's purely coincidental. Okay, so this is the grams of hydrogen in grams sample. The sample is 153 grams. So times 153 gram sample is 7.72. 7.72 grams of hydrogen in that sample, in 153 gram sample. Okay. All righty. See if I can remember how to do this one. (22) Each molecule of testosterone contains 9 atoms of carbon. Okay, 9 atoms of carbon, 19 atoms of carbon. So we got 19 atoms of carbon per 1 molecule of testosterone. Right, that's given. I don't know if I'm going to need that yet, but I put it up there because I like to extract information from word problems because they're meant to confuse. The mass percent of carbon in testosterone is 79.12%. 79.12% carbon. Okay, what's the molar mass of testosterone? All right. So molar mass, abbreviation, is equal to mass divided by moles. So what we need is the mass of the molecule of testosterone divided by how many moles that represents. Well, this is that percentage carbon maybe we can start from here. The reason being, this is atoms of carbon. (19 atoms of carbon weighs how much? If we convert atoms of carbon to moles of carbon, right? So that's 6.022 times 10 to the 23rd. I'm not cheating, looking at my, I'm trying to work this out myself. So that gets rid of atoms of carbon and leaves us with moles of carbon, right? So how about moles of testosterone? Well, it doesn't tell us that, does it? Oh, 19 atoms of carbon per molecule of testosterone. So that's moles of carbon. How about moles of testosterone? You know, I think I'm going at this the wrong way. If this is how many grams, this is how many grams per 100 grams of sample. This would be 79.12 grams of carbon per 100 grams of testosterone, right? That's the sample, 100 grams of testosterone. I think this would probably be better. Yeah, I'm gonna have to look at the sheet. Yes, I'm drawing a blank. Where about the rivers? 22. This one always stumps me. I was headed in the right direction with this one. It was atoms of carbon per molecule. So how many? Okay. Let's get rid of this for now. Let's focus on the carbon. This is 12.01 atomic mass units per atom. Right? So that gets rid of atoms here. Thought I had that clearly in mind. That would be atomic mass units for molecule. Oh, okay. Let's do this calculation first. This will be 19 times 12.01. I'm sorry? 12.01 times 19. Atomic mass units. Yeah. That's per atom. So 19 times that would be that many atomic mass units per molecule. 2.28 times 10 squared, or 228. 228 atomic mass units per molecule. And this is atomic mass units of carbon. Okay. Atomic mass units per molecule is the same as grams per mole. Right, isn't it? Yeah. Atomic mass units of carbon per molecule is the same as grams per mole of testosterone. Remember, in the periodic table, we first looked at atomic mass units per atom. And then we made the conversion. That number is exactly the same as grams per mole of the atom. Atomic mass units per molecule is the same as grams per mole of the compound. So that gives us grams of carbon per mole. All right, how many grams does that represent for the testosterone? If we have grams of carbon here per 100 grams of testosterone. So that's 79.12 grams of carbon for every 100 grams of testosterone, correct? Okay, so that cancels this one and leaves us with grams of testosterone per mole of testosterone. And that's what we want. You got the number?
It's 0.8.
Yeah, 288. And that would be E, be the best answer for that one. Yeah, I was trying to make it harder than it was.
Why did you get it?
Do what? Where did I lose you?
So, I think I figured it out. Basically, not the carbon 79%. I understand. It's a weird way that I understand it.
Okay.
Okay, because that goes out of the 228 because that's
That's what's throwing me off.
Oh, going from here to here?
The 228 then is multiplied by the percent average, right?
Yeah, once you make this conversion, once you understand that atomic mass units per molecule is the same as grams per mole, it's exactly the same.
So, but we went ahead with the answer and just did it by the percentage now. Okay.
And then we introduced the percentage here because that got rid of the carbon and put in the testosterone because that's what we need. We need mass of testosterone per mole. So we need mass of testosterone per mole. So that's what we eventually got here, here, and here.
Because the 19 atoms, 0.01 is 2 for neg, right? So
Right. Atomic mass units of carbon per molecule.
That's what's out of it. So
Mhm.
that's the code for-
Yes.
Okay, yeah. That's what I did. I just.
That was 22. $24. Let's see. An oxide of iron has a formula Fe3O4. Okay. What mass percent of iron does it contain? Okay, well, this is easy enough. We need 3 times iron. What's 3 times iron? Or what's iron? I'm sorry, 55.85. That's in the numerator. It's also in the denominator. Because this is total. Plus 4 times 16 times 100. And that'll give us the mass percent of iron. And if we did it right, it should be 72%. Now we've done formulas before, right? And the compounds are neutral. So the charge of this one should be equal to the charge of that one, right? So this is -2, that's -8, right? So how do you get an even number out of an odd here? You can't have an even number of charge, right? It has to be 8/3. Well, this is a compiled formula. I think that this is in fact FeO plus Fe2O3. So that would give you 3 irons and 4 oxygens. It's a combination of 2 different compounds. Okay, ammonium chromate contains what percent nitrogen by mass? All right, the point of this one, 26, ammonium chromate. We need 2 of these because that's a +1 charge. Chromate is a -2 charge. So we need 2 of these. That's why the formula is that way. Well, what's the percent nitrogen by mass? The reason this one is in there is because this subscript says there are actually 2 moles of nitrogen in that molecule, or in that mole of compound. 2 times 1. Right? If you have 2 ammonias, ammonia here and ammonia here, with a chromate, then you got a nitrogen here and a nitrogen here. You need 2 of them. So in the numerator, you got 2 times 14.01. And in the denominator, do it again. Plus, that was nitrogen, wasn't it? Yeah. You have how many hydrogens? 2 times 4 is 8. 8 hydrogens. plus a chromium, which is 52.00. 1 times 52.00, and then plus 4 oxygens times 16. There you go, times 100. And if we do our math right, it should be 18.4%. Yeah, the trick here is to recognize that that subscript means there are 2 ammonias, which means 2 of these and 8 of those. All right, let's see. Empirical formula. You have trouble with empirical formulas? Okay. First of all, what is an empirical formula? Empirical formula is the simplest whole number ratio of atoms in a compound. So what? No, whole number. Whole number ratio of elements in a compound. So if we had a compound like this, its empirical formula would be that, right? It's a 1-to-1 relationship. It's the same thing for this one. Right? They have the same empirical formula. So the empirical formula is sort of an intermediate step to finding out what this is, because this is entirely different than that. Right? This is benzene, and that's acetylene.
Why isn't it just follow along? If they rotate each other,
They're not the same. They're not the same compound,
right,
but they have the same empirical formula.
right.
Right. Well, the empirical formula is a step on the way to determining what this is. You need two calculations to get to the molecular formula. You need to take the mass percent amount of each element in the compound to find the empirical formula. Then you need the true molar mass for the compound to find out what its molecular formula is. But this one only asks for the empirical formula, so we'll do that one. Carbon and hydrogen only. That's a hydrocarbon. So that means that we have 85.6% carbon. And what's hydrogen? If those are the only 2 elements in there, it's 100 minus that, isn't it? Okay. Yeah. Okay. Now here's the problem. What we want to do is find what's the simplest whole number ratio between the numbers of atoms of carbon and the numbers of atoms of hydrogen in that sample. This relates to mass. This is mass percent. That doesn't say numbers. So we've got to find a way to convert that into numbers ratio. But we can't work with these values because they're dimensionless. They're parts per 100. We need to make an assumption. If you're not given a mass for the sample, assume 100 grams. If you assume 100 grams, that means parts per 100. This is 85.6 grams in a 100-gram sample. This is 14.4 grams in a 100-gram sample. So we still have the mass ratio is the same as the percent ratio. But now we've got something we can work with and convert this into numbers or moles of each one, right? So we want to get rid of grams there and leave us with moles of each one. Carbon will be 12.01 and hydrogen will be 1.01. Okay, so 85.6 enter 12.01 divided into that, 7.127. That's moles of carbon. How about 14.04 divided by 1.01 is 14.26257. 14.257. This is carbon, this is hydrogen. But those are not whole numbers. The mole ratio is exact. Right? That's established, that's fixed. What we need to do is convert it into whole numbers. All right, so if we multiply or divide both of them by the same value, we still have the same ratio. So the simplest way to do it is divide all the way through every element you got by the smallest one. That's where you start. So we'll divide this one by 7.127, divide this one by 7.127. And that obviously is going to be 1. And the other one should be close to 2. Yep, that's 2. So the empirical formula is CH2. Okay. All right. The next one, 32, we're going to take that particular compound, the next. I'm sorry.
I just got the last part, so you didn't write the number.
Okay. This is 32.
Now, why did you divide them both by 7.127?
I'm working my way toward whole number ratios.
Because that was the answer of the.
Well, we don't write compounds, empirical or molecular formulas with fractional subscripts.
But why would you divide?
Divide by this number?
By carbon?
Huh? Oh, it doesn't have anything to do with this part. It has to do with the numbers. Divide through by the smallest one.
Okay.
Then that converts this one into 1.
Okay.
So,
Oh, gotcha.
and this one is something else. It just so happens that this one came out to 2. Sometimes it comes out to 1.33 or 2.5 or something like that. And then you have to do a further conversion. You got to get to whole numbers. All right, 32. The empirical formula of styrene is CH. Okay, we know that they're giving that to us. The molar mass of styrene is 104.1 grams per mole. So the molecular weight, or the molar mass, is 104.1 grams per mole of actual compound. All right, this is the mole ratio of carbon and hydrogen in styrene. It's the simplest mole ratio. It could be, if we multiply each of these subscripts, right, in this case it's 1 and 1, we multiply it by some value here, and we find out what that X is, then we can find out what the ratio is for the molecule. Right? It's like that C6H6. We reduced it to a 1-to-1 ratio, right? So this would be the same for benzene or acetylene. But this is styrene. It's a different compound. So we need to find out what that multiplier is. Okay, what we're looking for is the ratio of molecular weight to what I call empirical weight. What's the weight of this right here? It's 12.01 and 1.01, right? 13.02. Right? So if we divide this and this, the nearest whole number is going to be X. Right? Because if this unit right here is 13.02, then if we multiply it by 1, right, that's molar mass is not right. Multiply it by 2 is 26. Multiply it by 3, it's 39. We're still not there. So we're looking for that multiplier by ratioing the true molar mass to the empirical mass. So let's find out what that is. 104.1 and 13.02. That's really close, 7.995. That's really close to 8. So if X is 8, our empirical formula is C8H8. And all you have to do is calculate the molar mass for that one, and it should be very close to that one. Okay. That's the trick for finding X, is ratio the molecular weight. You have to be given the molecular weight. There's no way around it. And the empirical weight of this empirical formula. Ratio them and you find out what your X is. All right. I'm not sure why I've got 33 in there, because it's the same procedure as we did for the others for finding the empirical formula. Right. I'll set it up for you, and then we won't go all the way to the end. For 33, adipic acid. It's one of the fatty acids. Right. Have you had any biology or anatomy and physiology talk about fatty acids and true fats? Okay, they're triglycerides. In other words, they're esters of fatty acids and glycerol. Yep. Okay, so this adipic acid has a composition of 49.32% carbon, 4384, 84%. Oops, that's not right. The way we write these types of compounds, carbohydrates, we do carbon, hydrogen, oxygen, not carbon, oxygen, hydrogen. So I'm going to put the hydrogen here, 6.85% hydrogen, and then 43.84% oxygen. And we do the same things we did before. Assume 100 grams. That makes this 49.32 grams of carbon, 6.85 grams of hydrogen, and 43.84 grams of oxygen. And then we just convert each one to its respective number of moles, and that will give us the mole ratio in the compound. Carbon's going to be 12.01 for every mole. Hydrogen's going to be 1.01. And oxygen's going to be 16. Okay? And that gives us some values. I might as well do them. Are we good so far? I didn't mess something up.
No, I'm just wondering why does it matter if the hydrogen comes before or after the carbon? Because I thought that just come first.
It doesn't matter.
Okay.
Right. When you write a carbohydrate, and your answers will show you that it's carbon, hydrogen, oxygen.
Yeah. I just know the acid except the H first.
First, yeah. This is not an acid. I mean, this is an acid, but this is right. This is the empirical formula. Okay. If we could write it a different way, that would show us where the acid hydrogen is located. But this is empirical formula, so we're gonna go with carbohydrate format. Yeah, that's a valid point. If it's an acid, we ought to have at least one hydrogen sticking out front, shouldn't we? Yeah. Okay, so if we do the math here, 49.32 and 12.01, that's 4.107 moles of carbon, and 6.85 enter 1.01 divided 6.78, 6.782. And then the last one, 43.84 for oxygen divided by 16 is 2.740. So the smallest one here is 2.740. We're going to divide everything through by the smallest one. And that's about 2.5 rounded off. By the time we get to this point, rounding down as to, oops, it's not right. 740. There we go. Rounding to the nearest fraction is 2.475. That's very close to 2.5. I should do this like that. And this one, let's see what it's going to be. 4.107 and 2.74. That's about 1.5. Okay. So how do we get rid of these fractions? This ratio is fixed. It's the same as that one. This is the same. 1 to 2.5 to 1.5. Multiply by 2, right? 2 times 1.5 is 3. And 2 times 2.5 is 5. And 2 times 1 equals 2. So this is carbon, hydrogen, oxygen. The empirical formula would be C3H5O2. At this stage of the game, when you write the empirical formula, trying to find the acidic hydrogen and putting it out there doesn't make any sense, because this is not the molecule. This is the empirical formula. Once you have the molecular formula, then you can figure out, which one's the acidic hydrogen and stick it out there in front. In fact, adipic acid is probably a carboxylic acid. So it's going to have something out here, then it's going to have a carbon like that, and there's your hydrogen. So what you would do is take that COOH group, and once you find out the molecular formula, yank that one out of it and see what's left, and then stick that one on the end. That's what I do. Okay, pencils have stopped. All right, that was 33. What are we doing on time? We got till 5, don't we? Since we're not doing a lab. I hope that's enough time. Vitamin C, ascorbic acid. Actually, it's vitamin C that works in our body as L-ascorbic acid, one of the isomers. We used to use vitamin C in chemical analysis too. It's a really good reducing agent, but neither here nor there, I guess. Vitamin C contains carbon, hydrogen, oxygen. It's known to contain 40.9% carbon, 4.58% hydrogen by mass. The molar mass of vitamin C has been found to be about 180 grams per mole. Okay, we're going all the way to the molecular formula with this one. Okay, so carbon, hydrogen, oxygen. Carbon, hydrogen, oxygen. We're given carbon at 40.9% by mass. Hydrogen at 4.58%. What's the oxygen? Well, the compound only has carbon, hydrogen, and oxygen.
Wow. Oh, you added those together.
Yeah, these two subtracted from 100 is that. Okay, now we do the same thing. 40.9 grams, 4.58 grams, and 54.52 grams. And convert each one of these to its molar equivalent. Then we can establish the mole ratio. Grams on the bottom, moles on the top. This is 12.01. This is 1.01. This is 16. I bet you could write a spreadsheet. If you did a lot of these and you knew that there were only going to be carbon, hydrogen, oxygen, nothing else, you could write an Excel spreadsheet and you just plug in these numbers and there it goes. Spits out the answer. Okay, so let's do the math. 40.9 divided by 12.01 is 3.45. 405. There we go. 4.58 divided by 1.01 is 4.535. 4.535. And 54.52 divided by 16 for oxygen is 3.408. So what's the smallest one in here? Well, these two are almost the same. If we divide by 3.405, this one's going to be exactly 1, and this one's going to be so close there's not much difference. But what's that one? 4.535 divided by 3.405 is about 1.33. That's the closest we can get there. So how do we get rid of that fraction? Yeah, 3 times a third, right? Gives us 1. 3 times 1 gives us 3, and the total is 4. So we multiply times 3, and that's 4, times 3, that's 3, times 3, and that's 3. So the empirical formula is C3H4O3. Okay, but we're going to the molecular formula, so we need to find out what X is. We're given 180 grams per mole. 180 grams per mole is the molecular weight. The empirical weight is 3 carbons, 3 times 12.01, 4 hydrogens, 4.04, and 3 oxygens, 48. So that's 88.07. 88.07. So we ratio those two, and I get very close to 2.
It doesn't say anything about empirical formula for weight. I don't think we want to do that. How would I know to do that?
No, it doesn't tell you in the problem. That's part of the solution. Now, if you want to find where that came from, either.
I'm just saying, like, how would I know? Like, how would I know to do the whole numbers? Why would I see?
Oh, because 1.33, and 1
Right.
is true, but we want whole numbers. Yeah, because we're thinking in terms of not just moles of each. We're thinking of atoms of each, and you can't have a third of an atom. Yeah. So then,
empirical formula is like an actual formula, but it's really not. It's just.
Yeah, it's a simplified version. Right. It's reduced to the smallest whole number ratio. So we're looking for this multiplier.
Molecular formula is just that X right there.
The molecular formula is whatever this is times each one of these.
Okay.
And we found out it's very close to 2. So the formula is 6, 8, 6. What is that? Vitamin C.
How do you know? Where's that 190 grams?
It's in the problem. All right. That was 34. We're still in chapter 3. Now, chapter 4 review is shorter, but still. That's the empirical weight. If you take the empirical formula, C3H4O3, and calculate the weight as if that were 1 mole. Calculate the weight, just add up 3 times carbon and 4 times hydrogens.
Right.
That's what you get.
Is what anything, 80,
Yeah, 8807.
so it's 180 divided by 88.
Yeah. We're trying to find out what X is. What's the multiplier? And the mass of the compound is 180, and the mass of the empirical formula, which has been reduced by a whole number value, is 80 or 88. And that's what your X is. Yes. 36. It's like I'm gonna kill another marker before we're done. How many of the following are true concerning balanced chemical equations? All right. Well, let's look at 1, 2, 3, 4. We have a 5. Yeah, we have a 5. How many of these are true? The number of molecules is conserved. Is that true? How do we know the number of molecules? It's the coefficients. The coefficients tell you the number of molecules. And all you need is one example that doesn't conserve and is balanced to disprove that statement, don't you? So let's try. Yeah, go ahead.
No, it's okay.
Balance that one. Hydrogen, oxygen yields water. We need 2 here, 2 here, right? Right. 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens. Okay, that's balanced. Right? 2 plus 1 is 3 molecules. Right? We didn't conserve molecules there. So that A statement, that first statement is false. You don't conserve the molecules, you conserve the atoms of each element on each side. If we tried to put a 3 here, that would give us 6 hydrogens, and where did the other 2 hydrogens come from? Just out of thin air.
Back, I'll figure out like which one's like the nearest, like, I don't know, never mind.
Just thinking out loud, right?
Yeah.
That's one of those cases. All you need to do is find one example that's false, and the whole premise is gone. 2, the coefficients for the reactants tell you how much of each reactant you are given. All right, that's a play on words. Much here means mass. Right. The coefficients don't tell you what the mass ratio is. They tell you what the numbers of molecules and atoms ratio is. All right, so that one's false also. It says nothing about mass. Remember that prime directive? When you have a balanced equation and you want to do stoichiometry, you can't go anywhere unless you're in moles. If you've got mass on this side, and you want to go to this side, you're stuck. Unless you convert to moles, then you can move. That's because the ratio that's in the balanced equation is mole ratio, numbers. 3, atoms are neither created nor destroyed. That's always been true. Coefficients indicate the mass ratio. Well, that's another way of saying 2 is false. The sum of the coefficients on the reactant side equals the sum of coefficients on the product side. That's like number 1. It's false. The coefficients on either side don't necessarily add up, and they didn't in our example either. So it's just 1, right? Only 1 right answer. (36) 37. In balancing an equation, we change the blank to make the number of atoms on each side of the equation balance. Coefficients, yeah. Right, change the coefficients. Right, after you write the formulas of each of your compounds and elements, whatever the case, you can't change their formulas. Right? You have to balance by coefficients. Because if you change the formulas, what are you doing? You don't have the same compounds or elements in there anymore. That's commonly called cheating. And it happens. Especially with new students. My physical science students try to do it all the time. Because it's not, chemistry is not the total thrust of physical science survey class. You got physics and chemistry and astronomy and geology and a couple others in there. And so we just kind of have to skim the tops of the waves. And that exercise throws them a curve almost every time. 39. What's the coefficient for oxygen when the following equation is balanced? All right. Let's see. I better put it maybe over here. Ammonia plus oxygen. Ooh, this looks like a combustion. We're going to burn ammonia and oxygen. You know that can be done? Oh, yeah. Plus water. And water's a gas in this case, so I suspect this is exothermic. It's a pretty hot reaction. All right. So if we want to balance this, we could try it without the budget method, but it's probably a good idea to stick with the budget for now. So we've got nitrogens, hydrogens, and oxygens. That covers everybody. On this side, we've got 1 nitrogen, 3 hydrogens, and 2 oxygens. On this side, we have 1 nitrogen, 2 hydrogens, and 3 oxygens. Okay. Now, what's the one trick? One of the tricks, hints. You've got an element here. Leave it to last. Don't put any coefficients in front of that until you have to. Because the coefficient in front of this only changes the oxygen. And doesn't send you down the rabbit hole chasing some other element. Okay, so nitrogen's already balanced. Let's go to hydrogen and see what that gets us. So if you've got 3 on this side and 2 on that side, and the hydrogen occurs in only one place here, only one place here, then there's another trick. Cross multiply. So we take this 2 over here, and take that 3 over here, and that gives us 6 hydrogens on both sides. Right. But it also messes up the nitrogens here, and it messes up the oxygens here. Let's see, 5. Right, 3 plus 2 is 5. Okay. Now we need 2 nitrogens on this side. That mess up oxygen again. Right, 4 and 3 is 7. Okay. So far, so good. Am I losing you? Now we've got oxygen that we need to deal with. It only occurs in one place. And we've got 7 versus 2. How do you get 7 out of an O2? Use a fraction as an intermediate step. Right? We want 7 oxygens on this side. So if I use 7 halves, right, we take a half of that oxygen times 7 is 7 oxygens, right? So technically, yeah, right. You have oxygen, oxygen. That's 4, 5, 6, 7. This is your oxygen molecule. We got 7 of them, right? We got 7 right there. But we're going to take a half of them. 1, 2, 3, 4, 5, 6, 7. That's 7 oxygen atoms. Okay. That's a trick. And now we got to get rid of that fraction. So how do you get rid of a fraction? Once you've got the established ratio for your balanced equation, this is technically balanced, right? It says so right there, 267, 267. But to get whole numbers, now we can multiply or divide through the whole equation by any number, and the ratio will still be the same. Just math. So what we're going to do is multiply by 2. If we multiply by 2, that gets rid of that half, right? But it also makes this one into a 4, and it makes this one into a 4, and it makes this one into a 6. And that 2's gone. So our ratio is 4, 7, 4, 6 coefficients. And what was the question? What's the coefficient for oxygen? 7. Okay. Now I could have done what your book said, balanced by inspection. It just turned you guys loose to the wind. But no, I couldn't do that. I want to at least give you a fighting chance against these things.
The answer is
7. The coefficient for oxygen was 7. Because we multiplied through by 2, got rid of the half fraction, and that left us with 7. Yep. 40. Let's scooch it up a little bit. This one's a little more difficult. Okay, so we're starting off with sodium amide, NH2, and sodium nitrate, saltpeter. Put that in gunpowder. Actually, potassium nitrate works too. I think potassium nitrate's more effective, but it'll work. And then NaN3. I think I'm going to run out of room. Hold on a second. Let's start over here. Sodium NH2, and then leave a gap for coefficients. Sodium NO3, and then sodium azide. This is what they put in no, not this one. Sodium azide is what they put in it's crash bags in your cars. The inflatable ones, airbags, yeah. They put that in there. All you have to do is send a little electrical shock through it, and it decomposes into nitrogen gas like that. That's what makes it go like in milliseconds. And that's what makes it kill your kids and small animals if it's not used right. And then let's see, ammonia. Okay. So we're definitely going to need the budget method for this one. Sodium, nitrogen, hydrogen, and oxygen. And notice that this nitrate changes, right? There's no nitrate on this side. So we can't use that trick where you have this balancing unit. We got to bust everything apart into elements. All right, so we got 2 sodiums here. We got 2 nitrogens, 2 hydrogens, and 3 oxygens. And I like to check myself too. What's that? 6, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I counted for all the elements. On this side, we've got 2 sodiums. Nitrogens, we got 4 nitrogens. We got hydrogens, 1, 2, 4 hydrogens, and oxygens, only 1. Okay. Well, we're definitely not going to start with sodiums. Right? because they're already balanced. Nitrogens, maybe. You have 4 nitrogens. The problem is, nitrogens occur in 2 places here and 2 places there. So what if we look for hydrogens? Hydrogen occurs 1 place here and 2 places here. How about oxygens? Oxygen's there, and only 1 oxygen here. What if we try that? Right, if we do this, right, that gives us 3 oxygens here. It also gives us 4 sodiums, right? And 6 hydrogens, right? So am I still good? 1, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17. So that's 10 and 7, 17. Okay. I was just checking myself, be sure I didn't create any elements. Okay. If we've got a,
Wait, how'd you get 6 hydrogen? Because you already have 4, but you added 3 more, so that is 7.
well, 3 hydrogens here and 3 hydrogens there is 6. I did a recount.
Oh.
I didn't just add.
I didn't count the other
Yeah.
sodium. I got it.
Okay, what if, let's see, sodium and hydrogen if we had what if I put 2 sodiums here, that gives me 2 more nitrogens, but that's only 3 nitrogens. What if I put a 4 here? Yeah, I think this is one of those cases where we're going to have to put 2 coefficients at the same time to make things work out. So, I'm making this more difficult than it is, I know. This happened to me the other day. This is a really freaky one. See if I'm barking up the wrong tree. All right. Right, sodium's 3 plus 1 is,
What if you just put a 3 in front of the first over here?
Yeah.
Would that be balanced? Maybe
that would give us
4 sodium.
3, 4. That would give us 3, 4 nitrogens,
6 hydrogens. 'Cause
6 hydrogens.
And then it's balanced.
Yeah, that was too easy. But it can get really ticklish, right? When you have elements in lots of different compounds, same elements spread out.
Yeah.
That can get really weird. Okay, let's move on.
Hold on.
Oh, okay. I'll scroll to the next one. Are you on 43 already? What are you looking at? Oh, some of the coefficients. Yeah. Let's see. 3, 4, 5, 6, 7, 8, 9. Yeah, that's right. No, just add the coefficients up. Yeah,
Oh.
there's understood 1 in front of the other guys. And that adds up to 9. 43. This one is a little more behaved. When the equation C6H14, that's a hydrocarbon. It's let's see, hexane is burned in oxygen. C6H14 plus oxygen yields carbon dioxide plus water. Always. When you burn hydrocarbons in oxygen, you always get carbon dioxide and water. Smallest set of integers, the sum of the coefficients. Okay. In this case, we've got carbon, hydrogen, oxygen. That's it. So there's 6 carbons here, 14 hydrogens, 2 oxygens on that side. And we have 1 carbon, 2 hydrogens, and 3 oxygens. We're going to save oxygen till last anyway, so we don't have to worry about that even odd thing. So let's go to the carbons first. Like 6. That gives us 6 carbons. And 13 oxygens. Okay. How about hydrogens? If we want 14 hydrogens on this side, we need a 7 there, don't we? And that gives us 7 plus 12 is 19, correct?
Oh. You just see 8 over there.
Well, let's see if I did it right. All right, 6 carbons. Let's see. 6 plus 12 is 18. 25. And 14 is 39. 39. Yeah, okay, so that's the right number. 6, 14. Oh, now we can do the oxygens. We need 19 on this side. Use the fraction again, yeah. So that gives 19 here. And then all we have to do is multiply by 2. Get rid of this fraction. That makes this one a 2, this one a 12, and this one a 14. So was it the sum? Yes, the sum. 2 plus 19 plus 12 plus 14. Right? 16, 17, let's see. 13, 14, 15, 16, 17, carry the 1, 4. 47? B.
What is that?
That's the total of the coefficients. That's what the question asked.
Yeah.
You still working on it? Okay.
Okay.
All righty. Those are fairly well behaved, those burning hydrocarbons. You know, burning carbohydrates works okay too. Like you take table sugar and burn it. You know you could do that? Yeah, just put sugar in a spoon and get a butane lighter underneath it and heat it up. Eventually it'll catch fire. It'll just be burning. That's what we do in our bodies, only we do it in steps. So we don't burn up our cells. But the end product is the same. The overall reaction is exactly the same. Whether you burn it quick or burn it slow. Okay. 44. A reaction occurs between sodium carbonate and hydrochloric acid, producing sodium chloride, carbon dioxide, and water. The correct set of coefficients respectively are blah, blah, blah. Okay, for this one, you got to know how to write those compounds. If you don't, then you can't balance the equation. So sodium carbonate is what? Sodium O3, right? And this is a 2 minus, and that's a 1 plus, so we need 2 of those. Right, so there's the sodium carbonate. Hydrochloric acid. Well, technically, hydrochloric acid is aqueous. So this is probably aqueous too. And that yields what? Sodium chloride, right? That was simple enough. in aqueous solution.
Or you could like,
Oh, I was prompted by hydrochloric acid. If this were a gas, hydrogen chloride. But if you dissolve it in water, it becomes the acid. Changes the name. What else? Sodium chloride, carbon dioxide, and water. CO2 is a gas plus water. I'm not sure. Maybe it's a liquid. Okay. We need to balance this one. Okay. So sodium, carbon, oxygen, hydrogen, chlorine. That should cover everybody. 2 sodiums, 1 carbon, 3 oxygens, 1 hydrogen, and 1 chlorine. On this side, sodiums. 1 sodium, carbon, 1 carbon, oxygens, 3, right, 2 here and 1 there. Hydrogens, 2, right here, and chlorine, 1. Okay. There are no elements in there that we can hold out till last. What I usually say is if you've got water in the reaction, save the water till next to the last, if there are any elements. So we'll try to stay away from that one right now. Sodiums, we could do 2 sodiums. How about that? And that makes 2 chlorines. Oops. What am I doing? Big dummy. So then I would put 2 over here to make 2 chlorines. And that gives me 2 hydrogens. So 2 hydrogens are good. 3 oxygens, 1 carbon. Oh, we're balanced. That's the nice thing about the budget. You can see instantly whether you're balanced or not. Okay, so we want the coefficients. 1, 2, 2, 1, 1. D. All right. Some of these are so simple, you can probably do it without the budget method. All right, 45. Chemical reaction has the equation 2AB equals C. So 2 A's plus 1 B yields 1 C. The question is, which of the following figures best illustrates a stoichiometric mixture of A and B? Okay, stoichiometric mixture is 2 to 1, right? That's before the reaction. Right, so if there are any C's in there, throw it out because the reaction hadn't occurred yet. The mixture is stoichiometric here. And what would happen after the reaction is all these would be gone and you'd have 1 C. So we can throw out 4, right? It's got C's in it. It won't count. What we're looking for is the ratio of 2 A's for every B. So let's see. First one, Roman numeral 1. 1, 2, 3, 4, 5, 6, 7, 8. So we got 8 A's and 1, 2, 3, 4 B's.
so the even.
No,
It's 2 to 1.
ratio here. 2 to 1 is stoichiometric.
I mean, like, if like there's a B for every 2 A's, like.
Correct. Right. It's 2 to 1. So if we have 8 A's and 4 B's, that ratio is 8 to 4 or 2 to 1. Right. So number 1 works. Right. How about number 2?
No, it's 8 to 8.
Okay. So 2 is 8 to 8.
And 3 is 4 to 8. It's 1 to 2.
That's wrong.
Right.
Oh, but different.
And 4 has C in it, so it's wrong. Yeah, so just the 1. Just this one. Roman numeral 1. That's the only one that satisfies the stoichiometry. All right, 46. Have y'all ever had any lab courses before?
I'm having biology, and I will do it.
Oh, okay. So some of the equipment that we were going to use in this lab, you may not have ever used, like a Bunsen burner. Okay, good.
I'm
Yeah. Using a balance, right? We were going to use these triple beam balances, but after this, you'll never use them again, right? Always use the top loading electronic balances. Okay. I'm just commiserating. How about 46? A 7.11 gram sample of potassium chlorate was decomposed according to the following equation. How many moles of oxygen are formed? So here's our controlling balanced equation. Potassium chlorate. Yeah. Yields 2KCl and 3O2. This is already balanced, I think. 6 oxygen, 6 oxygen, 2 Ks, 2 chlorines. Yeah, it's balanced. All right. We're starting off with 7.11 grams of potassium chlorate. And we want to find out how many moles of oxygen are produced. Right? We can't get there from here. That has to be changed to moles. And since there's only one reactant and we're assuming complete decomposition, we don't have to worry about a limiting reactant because there's only one of them. So if we convert all of this into that will answer our question. Right? How many moles of potassium chlorate do we have? Magic number? No. Molar mass of potassium chlorate. Right? You want to convert this grams into that many moles. You need the relationship between grams and moles.
You didn't know the 6.02?
That only converts one number of things into a different number of things. We're going from mass to moles.
Oh, we need the mass for the.
Oh, did you do the?
For 16?
What's potassium is 39? Huh? No, you need the molar mass of potassium chlorate. So K
16 times 3.
39.10. Right. 39.10 for potassium. Chlorine is 35.45.
Oh, okay.
And 3 oxygens, 48. So that's 122.55.
You don't have to multiply by 2?
No. You don't use the coefficients until you're converting moles of this to moles of that.
It doesn't multiply.
Mm-mm.
Like, you know how if you have the parentheses around it and you have another subscript?
Not for this one. No. You just use that amount. The 7 grams of this is how many moles.
Okay, I thought it multiplied.
So we divide 7.11 by that number. I get 5.80 times 10 to the minus 2. Moles of potassium chlorate. Now we can convert to moles of oxygen. And that's where you use the coefficients. We want to get rid of potassium chlorate and leave us with moles of oxygen. And the ratio is 3 of these for every 2 of those. So 3 times that value and then divide by 2. 8.70 times 10 to the minus 2. 8.70 times 10 to the minus 2 moles of oxygen. Oh, it's in standard notation. All right, so let's do this, 0, 0, 0. Move it 2 places over. Right, 1, 2, right here. So we don't need that one. 0.0870. D. Okay. Did I lose anybody?
I don't understand, like, once you got the. Yeah, the 3 and the 2, I don't understand.
3, 2.
So there's whenever you do the.
3 oxygen. The ratio in this balanced equation between the potassium chlorate water, oxygen, for every 2 moles of KClO3, you get 3 moles of oxygen. For every 2 moles of this one, you get 3 moles of that. We're using it as a conversion factor.
Why do you do 3/2?
Because I want oxygen on the top. And I want to cancel. This is
Okay.
for every 3 moles of that one, it takes 2 moles of that one. I should have written in the moles. Sorry. And this cancels moles of that, and leaves us with moles of oxygen. Right? Dimensional analysis again. Okay.
You're fine with all that. I'm just getting the. I want to say.
Oh, okay. Uh, 47. How many grams of calcium nitrate can be produced by reacting excess nitric acid with 6.33 grams of calcium hydroxide? All right, so this is an acid-base reaction. We're going to react nitric acid with calcium hydroxide. And these are aqueous, right? It doesn't say, but I know they are. And one of the products it says is calcium nitrate. Now, why did I do that? Because that's a -1 charge and this is a +2. This is a -1, this is a +2. So I know that. What's left over? I don't know if I mentioned this before. Whenever you react an acid with a base, you always get a salt in water. Always. So now we can balance this. The nitrates are going to stay the same. Right, we can use them as a balancing unit. There are 2 nitrates on this side, so we need 2 nitrates on that side. There's 1 calcium, 1 calcium. Now, what do we do with the hydroxides and the hydrogens? Well, if we got 2 hydrogens here, and we got 2 hydroxyls, right? Look what that does. That gives us 2 HOH, or H2O. 2 waters.
So, based off the question, I wouldn't have known there was water. I would just have to know that because it's an acid in the base.
Yeah. I think that's why I put that in the review, because we may not have covered it in the lecture. And this gives me an opportunity to make that point.
Okay, so acid.
By definition, this acid, whenever an acid combines with a base, it always gives you salt, a salt in chemical terms, and water. Not just table salt. It's a combination of this cation and that anion is a salt. Most of those
Will
salts,
I have to recognize this as salt?
you just have to know that when you react an acid and a base, you always get a salt and water.
Right.
But once we get the equation balanced, then we can do something with it. Which is what? 6.33 grams of this one. And what are we looking for? how many grams of calcium nitrate can be produced if this is in excess. So we got plenty of it. We're going to consume all of that and make this. Right? So are we balanced? Oh yeah, I think we're balanced. We put a 2 here and a 2 there. So how many moles of calcium hydroxide do we have? We need calcium, right? It's 40.08. Right? We need the molar mass of that one. 40.08. 2 oxygens and 2 hydrogens. Right? 10, 1, 4, 7, 74.10. So if we divide 6.33 by 74.1, I get 8.54 times 10 to the minus 2. 8.54 times 10 to the minus 2 moles of calcium hydroxide. Okay. We need to know how many moles of this we have so that we can convert it back to mass, because it asks us how many grams of calcium nitrate. Well, notice this is a 1 and this is a 1. So that value, moles of calcium hydroxide, is exactly equal to calcium nitrate. So we have 8.54 times 10 to the minus 2 moles of calcium nitrate. We just need to convert that to grams of calcium nitrate.
How do you know that you have that?
Because that's 1 and that's 1.
I know, but I thought that the 8.54 was for the calcium.
Hydroxide.
Yeah.
That's right. So I just did this in my head. Right? Calcium hydroxide. And we want calcium nitrate. Right? What's the ratio of moles to moles? 1. So that one cancels, leaves us with this one. It's the same number because the ratio is 1 to 1. Now I need a molar mass for calcium nitrate. Let's see, calcium's 40.08, 2 nitrogens, 14.01 times 2, and 6 oxygens, 2 times 3. So let's see what that is. Two and 16 here times 6 plus. Oops, I messed up. Let me try it again. There we go. 164.1 is the molar mass of calcium nitrate times 8.54 times. That's 14.0 grams of calcium nitrate. Okay, that's B. That was the total of each of these. All right, I've got 1 calcium, I got 2 nitrogens, and I've got 6 oxygens. Add them together, and that's 164.1. How are we doing? Got an hour and a half. Let's see, 52. Are we good? I'll start from this side.
You do that math, it comes out to
Did I do it right?
I'll take your word.
All right, 52. For the reaction, P4O10 plus 6 waters yields 4 H3PO4, phosphoric acid. What mass of P4O10 must be consumed if 3.71 times 10 to the 23rd molecules of water are also consumed? All right. So this looks different, but it's really not. This is just a stoichiometry problem. P4O10 plus 6 waters yields 4 H3PO4. Okay. We want to know what mass of P4O10 is consumed. So we want to know grams of that. If we start off with 3.71 times 10 to the 23rd molecules of water. All right. There are two approaches you can take to this, right? We've already got numbers, so we can move from here to there with molecules. But when we get over here, we got to convert it back to moles in order to use the molar mass to find out grams. But I think it's easier to make this into moles first. This gives us moles of water. Right? Molecule.
Use the 6.0.
Right. 6.022 times 10 to the 23rd. And that's 1 mole of water. Is that many molecules? So we divide that value into 3.71 to the 23rd. Yep. And we take Avogadro's number, divide it. There we go. Which is 0.616 moles of water. So we want to convert that into moles of P4O10. Moles of water. Right? What's the ratio? Well, 6 waters for every 1 mole of P4O10. So we cancel the waters, divide 6 into that value. Because the ratio between water and P4O10 is 1 to 6. 1 to 6. So I get 0.103 rounded off. 0.103 moles of P4O10. Now we need to convert that to mass. Moles, grams. We need molar mass of P4O10. 4 times, what's 32? No, 30.97 for phosphorus. And 10 oxygens. Okay. So 10 oxygens is easy, 160.
What's that number right there? 0.19.
Wait.
Yeah.
This one,
Oh, it was
0.103. Yeah. And then 30.97 times 4. And add those two together, I get 283.88. 283.88 times 0.103. And I get 29.2 grams. Nearest one is B, 29.1. Must be a rounding error somewhere. All right. Let's see. 58.
Get all the way over there, I think that. I have to write down the math, so I know where the numbers come from, what we're over.
Okay.
Because the 283 is throwing me off right now. So I have to-
That's grams per mole.
Yeah, so that's-
Yeah.
I'm good.
All right, 58. 5.95 gram sample of silver nitrate is reacted with the barium chloride according to this equation to give 3.17 grams of silver chloride. What's the percent yield? Remember what percent yield is? Percent yield. It's equal to the actual product divided by the theoretical product from the stoichiometry of the equation times 100. Okay. So we're given, we start off with 5.95 grams of silver nitrate. Silver nitrate solution. And they've already balanced the equation for us. Isn't that nice? Barium chloride yields silver chloride solid, 2 in front of it, yeah. And then barium nitrate plus barium nitrate in solution. So this is going to drop out of solution as a precipitate. We're going to catch it, dry it, and weigh it. And what we want is 3.17. Actually, what we got was 3.17 grams. Not the theoretical. The actual yield is 3.17 grams of silver chloride.
How do we know that's fact?
Because they say it is. According to this equation, to give 3.17 grams of silver chloride. Yeah. Mhm. We're starting off with 5.95 grams of silver nitrate. So what if this is 100% conversion from here to here, how much will that be? That's our theoretical. So we got to find moles of silver nitrate, don't we? So silver is what? Silver, 107.87. 107.87 grams per mole. And chlorine is 35.45. Just add those together. 1, 2, 13, carry the 1, 12, 13, carry the 1, 4, 1. 143.32. Turning dyslexic here. 143.32. There we go. Divide that into 5.95. I get 4.152 times 10 to the minus 2. Moles of silver nitrate. Okay. How many moles of silver chloride does that represent? The same, right? 2 to 2. Exactly the same amount of silver chloride. So now we need to convert moles of silver chloride into grams of silver chloride.
Wait, what did you do there with the nitrate into the fluoride? You just said it, but I'll. Okay.
2 to 2, 1 to 1. It's like before.
just trade it out.
Yeah, this is, they're exactly the same moles. If you know the moles of silver nitrate, you know the moles of silver chloride produced because it's 1-to-1, 2-to-2. Now we need to convert back to grams of silver chloride. So what was that? 107.88? Yeah, 87. There it is. 107.87. Yeah, 107.87. Now what I want to do. Oh, shoot. I messed up. Anybody see what I did wrong? Huh? This is the molar mass of silver chloride. That's silver, and that's chloride. So I was calculating the wrong one. I need to do this one first. Silver nitrate. So silver nitrate is 107.87.
Wow.
Because I've got to go from silver nitrate to silver chloride. So I got to convert it. I got to use a different molar mass. That's the wrong molar mass. This is silver, nitrogen. There you go. And then 48 for the oxygens, 3 times 16.
So 35.45 and the first one's fluorine. Yeah.
Right. This is the chloride. So I already put that one over here because we're going to need it anyway. 107.87 and 14.01. And then 3 oxygens, which is 48. 169.88. 169.88. There we go. Now I need to divide that into 5.95.
169.
Yeah, 169.88 grams per mole. And divide that into this value, and I get 3.502 times 10 to the minus 2 moles. Now, it's still the same, right? Whatever value we get here is the same as here because the ratio is the same, 2-to-2. So now I can convert this back into silver chloride by multiplying by 145.32. I get 5.09. Silver chloride. Oh, excuse me, that's not the answer. Percent yield. 5.09 is what I would expect to get from 5.95 grams of silver nitrate. That's the theoretical yield. 5.09 divided into 3.17 times 100. Okay, 62.3%. That's the percent yield of that reaction. Okay.
Did you multiply that 3.50 to, you multiplied that with the, you multiplied that with the 145, right?
Yes.
Okay, okay.
Right. Yeah. These are multiplied together. And then I had to continue and do this calculation. Okay, we got another stoichiometry here, 59.
Pay the top part.
Oh, that part, yeah. And yeah, 63.1. Okay. Let's see, we're going to combine methane with chlorine gas and give us carbon tetrachloride and hydrogen chloride gas. using that equation. What mass of carbon tetrachloride will be formed if 1.2 moles of methane react with 1.11 moles of chlorine? When you see 2 or more reactants and you're given exact amounts of each one, you can bet that there's going to be a limiting reactant. So let's operate on that premise. So we got methane plus chlorine gas yields carbon tetrachloride plus hydrogen chloride gas. Yeah. Okay, we're starting off with 1.20 moles of methane. And 1.11 mole of chlorine. Okay. Why did I stagger them like that? Because I'm going to do calculations across here.
Right.
The way to find the limiting reactant is to go to the product. If it is asking for something in the products, like what mass of carbon tetrachloride will form, then take all of that and convert it into this. And then take all of that and convert it into this. The limiting reactant is the one that produces the least amount. All right. So if we have 1.20 moles of methane, how do we convert that into carbon tetrachloride? Well, it's 1 to 1, isn't it? So we have 1.2 moles of carbon tetrachloride from that methane, if all of it is used. If we do the same thing with chlorine, right, so this is chlorine, and this is methane, then we want to get rid of the chlorine and leave us with carbon tetrachloride. Oops, that's done. CCl4 on top, Cl2 on the bottom. This is in the numerator, that's in the denominator. So the coefficient of chlorine is 4, and carbon tetrachloride is 1. So 4 divided into 1.11 will give us the other one. 0.278 moles of carbon tetrachloride. Right. So this is obviously the limiting one. It produces the least amount. That one's going to run out. And we'll have excess. This is limiting. And this is excess. So this one determines the extent of the reaction. And we're only going to get 0.278 moles of carbon tetrachloride. So what mass do we get? Now that we know how many moles we can expect, then we can convert to mass. Just multiply that one times moles on the bottom, grams on the top. So carbon tetrachloride would be what? Well, carbon is 12.01, and 4 times 35, 45 for the chlorine. That's 153.81. Times 0.278 is 42.7 grams. Was that the question? Yeah. What's the mass? D. D would be the answer. Let's see, we're off to 61 now. We're still in chapter 3. We good? You all right? Okay. All right, 61 says, which of the following statements is always true concerning a reaction represented by the following balanced chemical equation? All right, that's ethane. 2 ethanes plus 7 oxygens yields 6 waters and 4 carbon dioxides. Let's see. What do the answers look like? We have equal masses of C2H6 and O2. There's no limiting reactant. Okay, so let's write the balanced equation in here. 2C2H6, yeah, plus 7 oxygens yields 6 waters and 4 CO2. Equal, if the first one says if we have equal masses of C2H6 and O2, equal masses. So what's the molar mass of this right here? That's what I'm curious about. 2 carbons
24.
and 6 hydrogens. Right.
24 O2 plus 6 1.
Yeah. 308. Okay, so 1 mole of this is 30.08. That's grams per mole. Right? But it takes 2 moles in this reaction. So that's actually 60.08 grams in a stoichiometric ratio. Right? If we say mass to mass, it would be 60.08, and then 7 oxygens would be 7 times 2 times that. Okay, I'm talking stoichiometry now. So 7 times 32 is 22.4, 22.40, 22.40 grams per mole. Well, we got 7 of them. So that's 156.8. No, more than that. Hold on a second. Let me try that again. 22.047 times that. This is better. 154.28. All right. This is the mole stoichiometry. 2 of these for every 7 of those. But if we convert it into mass ratio, 2 moles of this, which is 60.08, and 7 moles of that, which is 154.28, exactly 60 grams of this will react with 154 grams of that. That's a stoichiometric ratio of mass. All right, now we can look at A. If we have equal masses, there's no limiting reactant. Well, if we have equal masses, right? If we triple this one or 2.5 times this one, then we're going to have a lot more of this one than we need, right? So oxygen would be limiting if we have equal masses. So A is false, right? A is false. We do have a limiting reactant. If we have an equal number of moles of C2H6 and O2, there's no limiting reactant. If we have an equal number of moles, say we have 7 moles of oxygen and 7 moles of C2H6, right? We've still got excess of this one because you only need 2 of them. You're going to have 5 moles left over, right? So B is also false. How about C? If we have more mass of C2H6 than O2, then O2 must be limiting. Right? If we have more mass of C2H6, if this is more massive than that one, then yeah, we have excess of this one, and O2 is limiting. That's true. So none of these statements is true. A can't be right, and we found our answer. Yeah, C. Yeah, what do they say? Numbers don't lie, only people lie. Okay, 62. Equal masses in grams of hydrogen gas and oxygen gas are reacted to form water. Which substance is limiting? So we need the reaction between hydrogen gas and oxygen gas to yield water. We did this one before. We need 2 of those and 2 of these. Okay. Now, if we have equal masses of hydrogen gas and oxygen gas, right? X grams here and X grams here. Well, let's find out what the mass ratio of each one is. Right, hydrogen is 2.02 per mole, but we got 2 of them, so it's 4.04 grams ratio to 32 grams, right? Okay, so if we have equal masses of each one, right? If we had 32 grams of hydrogen, there had to be more than enough, and oxygen would run out. So oxygen gas is limiting. Right. Water can't be limiting because it's a product. That's a dumb statement. Hydrogen is not limiting because if we have equal masses, we have more than enough hydrogen. D's wrong. More information is needed now. We got our answer. It's oxygen is limiting. If they're equal masses. Oops. I'm good. Okay. 62. One of these days, we're going to get out of chapter 3. For the reaction into 2H2 and into H4. See, this is 64. Into plus H2, correct? 2H2 yields into H4. That's dinitrogen tetrahydride. Actually, it's probably got a common name. I think that's hydrazine. If the percent yield of this reaction is 82%, 82% yield, okay, what's the actual mass of hydrazine? Well, there it is. Produced when 25.57 grams of nitrogen, 25.57 grams of nitrogen reacts with 4.45 grams of hydrogen. Okay. All right. With 82% yield, we can find out with this information what the theoretical amount of hydrazine would be. We just have to find out which one's limiting. And then once we find out that theoretical amount, we can apply this percent yield and find out what the actual amount is. Isn't that the question? What's the actual mass? Yeah. Okay. So let's convert this to moles. Right? Grams per mole, which would be 2 times 1402 is 28.02. Right? So that's how many moles of nitrogen. (25.57) enter 28.02 divide is 0.9126 moles of nitrogen, and convert that to hydrazine. Ratio is 1 to 1. So it's 0.9126 moles of hydrazine. All right, so let's take the hydrogen and convert it to moles first. So that's 1.2.02 grams per mole of hydrogen gas because it's diatomic. divide that into 4.45. And I get 2.203. 2.203 moles of hydrogen. Then we convert that into hydrazine, which is 1 here and 2 here. 2, 1. So divide that by 2, and I get 1.101 moles of hydrogen. All right. We can tell easily now that the limiting reactant is nitrogen. So what we need is to convert that back to grams so we can apply this percentage. Okay, hydrazine. 2 times nitrogen is 28.02, and 4 hydrogens is 4.04. $32.06. Times 0.9. So let's get it down there. There we go. Yeah. And 32.06 times that. And that's 29.26 grams. That's theoretical. What?
Where's that 32?
Right here. Okay, this is the theoretical. So if this is a percent yield, this is 0.82 grams actual per gram theoretical. Or you could write it 82 grams per 100 grams theoretical. Either way, it doesn't matter. It's the same fraction. And if we multiply that times 29.26 grams theoretical, then the theoretical cancels and leaves us with grams of actual. So
What are you doing with that? 32.00 divided by 1 mole. Did you multiply that by something?
this is 6
You multiplied that by.
times that value right there. See?
Okay, so you go back to that.
Yeah. I found out which one was limiting. This is the least amount. That's too much. This is the least amount. It's limiting. So now I use this to tell me the mass of hydrazine that's actually produced. See, theoretically produced. This is theoretical. This is the percent yield. So 0.82 times that is 24.0, rounded off. That's actually what you get out of a reaction. Okay. Anybody need a break? No. Want to get it over with? Let's get it over with. All right, we've only got till 5, don't we?
There's like 70 some questions. When we didn't talk about chapter 4 last week. Yeah.
You did the video, we didn't talk about it.
Oh, that's right. We did the video. Did everybody watch it?
I watched it, but it's harder to not be able to ask questions. It's very eyes.
What's the molar mass of tetraphosphorus decaoxide? So in order to do this one, and in the interest of time, tetraphosphorus, which is 4-phosphorus decaoxide, so P4O10. All you have to do is say 4 times phosphorus and 10 times oxygen and add them together. And you should get 284. Okay. Which of the following samples contains the greatest number of moles of carbon atoms? All right. So let me do the answer. Well, the answer is D. So let me just do that one. In order to answer the question, you have to do each one the same way and compare the answers. So if I do just D, 180 grams of glucose. C6H12O6. We want to convert that to, first, moles of compound. So we need 6 times 12.01, 12 times 1.01, and 6 times 16. And add those together. Did I do that right? I don't believe I did. 12.01, 6 times, and then 12, and there's 1.04 times. That's at that 180.18. Oh. So it's about a mole. But this is only moles of compound. And the question asked us greatest number of moles of carbon atoms. So we want to convert compounds to carbon atoms. Actually, we're going to compare. We don't have to go all the way to atoms. We can just say moles of carbon. And if we find moles of carbon for each one and compare them, then that's the same thing as going all the way to atoms. So what I want is moles of carbon. Carbon moles. Compound moles. What's the ratio? Well, for every 1 compound mole, you have 6 carbons. Right? So this is going to be 180 into that, which is about 1 times 6 is about 6 moles of carbon. And that one happens to be the greatest number of moles of carbon of all of those samples. And you just do the calculation the same way. You need, what's that actual value? What's the molar mass of the compound? And then what's the ratio of carbon to the total? Right? For the first one, it'll be 4 carbons. Second one would be 2 carbons. C would be 1 carbon. And you do that same calculation for each one and compare them. Oh, this is 69. All right. Let's see. Molecular formula of this molecule. All right, we've already done one of those. I'm going to leave 70 alone. Okay. 71. All right. Naturally occurring iron has 5.82% of the first isotope, 91.66, the second isotope, 2.19, and third isotope, and 0.33% of the last isotope. And the actual masses of each one are given there in sequence. So you just take 0, let's see, this is 71. I take the decimal equivalent of the percentage, 0.0582 times the first one, which is 53,940. Atomic mass units. Then I take the second one, 0.9166 times its mass, 55,935. And then the fourth one, 0.0219 times 56,935. Okay, and the last one, what's the decimal equivalent of that one? 0.33%. 0.0033. Right? Move it over 2 places. Yeah. times 57,933. And you get a value for each one. This is the contribution of each one of those isotopes to the total. You get a value, add them together, and they should be 55.85 total atomic mass units. That's the average atomic mass for that element, iron. Right? Does it agree with the periodic table? Yeah, it agrees. 85. Mm-hmm.
AMU stands for what again?
Atomic mass units. Your book might just put a U.
Yeah, that's what I have my other things to try to do.
Yeah, I prefer AMU. All right. 73 is in there just to reinforce the concept of what we mean by empirical formula. If you've got those molecules, A, B, and on down, you count up the carbons and the hydrogens in the first case, you have 6 and 6, right? So the simplest ratio is 1 to 1, CH. The second one is 2 carbons and 4 hydrogens. The simplest ratio there is 1 to 2. Then C, you add up carbons. I think there are 6 carbons, 12 hydrogens, and 6 oxygens. And the simplest ratio there is 1 to 2 to 1. That's glucose, I'm sure. Looks messy. We would normally write glucose like that. And then we got a CH2OH up here, and then we got an OH here, and an OH here, an OH here, and OH here. So that's 1, 2, 3, 4, 5, 6, 7. Well, there are other hydrogens in here somewhere. I think there's a hydrogen here. Yeah, there's a hydrogen here at each one of these. Right, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then 1, 2, 3, 4, 5, 6 oxygens and carbons. This is a carbon. That's 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 a carbon. So there's 6 carbons. That's the way we do it in biochemistry anyway. Okay, 73. Is there yeah, there's another one. Okay, this last one, how many carbons are there? 1, 2, 3, 4, 5, 6. So C6 H's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10 and O2, right? O2. So to reduce these to the least numbers, divide by 2. So we got a 1, got a 5, got a 3. 3, 5, and 1. That's how you do that one. Finally, chapter 4. Okay, we're starting over again. 1. An unknown substance dissolves readily in water, but not in benzene. All right, what's the difference between water and benzene? This is a polar solvent. This is a non-polar solvent. So like dissolves like. If it dissolves in water and not benzene, then the substance must be polar. That makes B's the answer. Which of the following is not a strong base? Number 5. Anytime you make a hydroxide out of an alkaline metal or an alkaline earth, right, first or second column, you have a strong base. Now, all of the alkali metals hydroxides are completely soluble in water. Sodium hydroxide, lithium hydroxide, potassium hydroxide, all those. The second column, say magnesium hydroxide, calcium hydroxide, strontium hydroxide, they're not completely soluble in water. But by definition, the chemical definition of a strong base is whatever makes it into solution is completely torn apart, right? It dissociates. That makes a strong base. So calcium, potassium, lithium, strontium, all of those are strong bases. C, ammonia, is a weak base. So by process of elimination, A, B, D, and E are strong bases. The only one left is ammonia, right? It's not a strong base. It's a weak base. And we'll get into that in more detail next semester. If I'm here and you come back. We got a whole chapter on acids and bases. Actually, I think there are 2 chapters. Yeah, in my book, there are 2 chapters. I'm not sure about yours. 6. Which of the following is paired incorrectly? All right. Strong acid, weak acid, strong base, weak base. All right. Let's start at the bottom. How about E? Ammonia, we just determined it was a weak base. Hydrogen chloride and when they say these are acid bases, you have to assume they're dissolved in water. Hydrochloric acid is a strong acid. Barium hydroxide. Barium is an alkaline earth. Yeah, go ahead. That's memorized. Yeah, there's a list in your textbook of the strong acids and strong bases. Yeah, and that's one of them. No, you won't have that with you. You gotta know it. Strong acids. The most common strong acids are hydrochloric acid, and these are all aqueous solution. Nitric acid is strong. Let's see. Perchloric acid is strong. In fact, I think chloric acid is strong also. No, just perchloric.
We just have to know that.
Yeah.
What about the strong bases and stuff?
Oh, those are easier. If the base is made from first or second column elements, hydroxides, those are all strong bases. Right. Alkaline metals or alkaline earths. The hydroxides are the bases. If they're hydroxides of any of those, they're strong. Okay. There's this one, nitric acid, sulfuric acid, and I think that's it. That's all you have to know. Those are strong acids. So HNO3 is listed as a weak acid. That's wrong. It's a strong acid. All right. 7. The man who discovered the essential nature of acids through solution conductivity studies is, you just have to memorize it. Should be in your book. That was Arrhenius. Arrhenius. Arrhenius, E. Yep. We'll get into more D. We'll see him again in second semester. 9. A 16.4 gram sample of HF is dissolved in water to give 2 times 10 to the second milliliters of solution. The concentration of the solution is, okay, the answers, you look at the answer and you see they're all in molarity. So you have to use the definition of molarity. Molarity is moles per unit volume, and the volume has to be in liters. Okay, so 16.4 grams, you need moles of HF. You can't use mass. Moles. That's my abbreviation for moles. Grams of HF, and we need a molar mass of HF. Right, so it's 1.01 for the hydrogen, and fluorine is 19. So it's 20.01. That's how many moles of HF we have. 16.4. And 20.01. Yep. That's 0.8196 moles. So now we can put that in here, 0.8196 moles. How many liters of solution do we have? We have 2 times 10 to the second milliliters, which is what? 2 times 10 to the second milliliters. How many milliliters in a liter? So if we want this unit to get bigger, that number has to get smaller. That means we got to move that direction. Which means we need to reduce that one by 1,000. Milli means 10 to the minus 3, right? So 10 to the minus 3 times 10 squared times 2.0. Right? This is 10 to the minus 1, correct? 2 and 3 minus 3?
Mm-hmm.
Okay. So 2 times 10 to the minus 1 is 0.20 liters. Right, so let's divide those together. Well, it should be 4.1 molar. Save some time. You know, a thought just occurred to me. If you guys took your exam in Brightspace, then we could use next week for the lab we missed today, and then follow up with the lecture and not have to take for that test in person if you want to do that.
The test on Brightspace will be like the same.
Yeah, I don't think I've made it into it's actually a document, PDF file. Let me check it just a second. Let's see. I have to stop the share. Yeah, you can take it on Thursday, or you can take it before midnight on Friday. Right, that's acceptable. Let's see. Go back to Brightspace. Oh, it's going to make me log in again. Doing what? No, we're going to do it next week. Instead of the exam, we'll do the lab first, and then we'll follow up with the lecture. A lot of students like it that way because you don't have the pressure and face-to-face. And your eyes will be hopefully better. Your eye will be hopefully better. Let me see. So it wants me to go back into here. I'm just checking to see where it is. I don't think it's a Brightspace quiz. All I have in the Brightspace quizzes are the reviews, I believe. Yeah, reviews. Okay, so what we're going to see is it's more like an assignment. So there's exam. It's exam 2, isn't it? Yeah, exam 2. There it is. In an assignment. Yeah, it's going to be a document, PDF file. So what you would do is just click on it. Let me go back into, let's see, is it available? Let me make sure it's available. I think it's available. Okay, let's go back into content. Let me be a student. Go back into content. And then go down to the module. Learning module, exam 2. Let's see if it's there. Let me collapse all that stuff. Okay. There it is. Oh, only available on the 22nd. If you want to take it you think you might want to take it early? Okay, so let me change that availability. Oh, that's right. So I can't get into it. Yeah. All right. So let's go back to quiz. No, not quizzes. Go back to assignments. That's what it is, assignments. And here it is. So let's edit. And availability dates. Here we go. So let me change that to, let's see, today's the 15th. What do you think? Maybe Tuesday or Monday? Monday. Okay. Now let me go back as a student and be sure it's available. Oh, it won't be available until Monday. All right. If you have any trouble, let me know. But what you do is you download that PDF file, and it looks exactly like that exam. And it should be a fillable form that you can save, put your answers in, and then save the form, and then upload it in that same module where you found it. There should be an upload button for the file, and that way we won't have to ditch this lab. You probably get hooked on taking the test at home anyway and insist that I do all of them that way. Well, yeah, it does that. Did we finish that one? We did finish 9. Here we go. Here we go. Yeah, we did. Okay. All right. 14. Yep. If we run out of time,
As long as you give us the highlight ones, we can, yeah.
I give you the answers and you can work on them.
And you gave us all the.
Oh yeah, I have right, work problems. Okay. So we'll run right up to the end of the clock. 14. What mass of calcium chloride is needed to prepare 3.95 liters of 1.49 molar solution? This solves the equation in the other direction. Right? If we know what the molarity is, we know what the volume is, then we can find out how many moles we need, and that then we convert it into calcium chloride mass. So we're solving for the number of moles actually.
So the base answer is the molarity?
Well, the molarity is 1.49 right there in the problem.
What does the base stand for again?
Volume.
Oh, okay, I thought you said molarity.
3.950. 950 liters. And this is the number of moles. 1.49 enter and 3950. So that's 5.89. 5.89 moles of calcium chloride. So now we can convert calcium chloride into grams with a molar mass. Right? Calcium is 40 point something, isn't it? 4008 for 1 calcium, and 2 chlorines are 3545 times that. Right? 35.45 enter 2 times, and then 4008, right? 40.08 plus 110.98 times 5.89. That's 654 grams of calcium chloride. Nearest one is 653 E. I always get caught by those rounding errors. All right. So are these types of calculations give you any trouble?
So barely.
Yeah, these are way easier.
Easier than the last chapter?
I thought the question was more out.
Well, yeah, it's more formulated. Right? Just right. You know what the molarity formula is, and you just plug in the ones you know and solve for the one you don't. 256 milliliters of 0.838 molar ammonium chloride. We want to know what the mass is that you've. So if molarity equals moles times volume, then molarity times volume equals moles. Right? And we know what molarity is, 0.838. Here, 0.838 molar. I don't know if I made this point before, but if you write that number like this, it's wrong. That's called an orphan decimal. We don't allow orphan decimals in this class. You've got to have it bracketed in by that zero. A lot of my students, apparently their high school teachers taught them that. Yeah. The problem with that is if you put it in a sentence, you might mistake it for a period.
My teacher would always not put an ability of wrapping.
Good. And that's why Europeans and the rest of the world, instead of using a period, they use a comma. So you don't get it mixed up with a period in a sentence. Okay, let's see. So molarity times volume. But the volume is in milliliters. How many liters is 256 milliliters?
256.
Wrong direction.
-3
256 milliliters.
times.
If the unit gets bigger, the number has to get smaller. Goes 0.256. Because milli means 10 to the minus 3. So 256 times 10 to the minus 3 is 1, 2, 3. 0.256 liters. 0.256, enter, and 0.838 times is 0.215. 0.215 moles. Question was mass, wasn't it? Yeah, mass. Ammonium chloride. Plus one charge, minus one charge, one of each. So we need the molar mass. Nitrogen, 4 hydrogens, and chlorine. Uh, 53.5. Zero. Yep. Times 0.215 is 11.5 grams. A. See how far I can get. $16. Good. Let me see. 74.28 gram sample of barium hydroxide is dissolved in enough water to make 2.450 liters of solution. Oh, this is a combination. We're going to make a concentrated solution and then dilute it. So the first thing you need to do is find out what's the concentration of the concentrated solution. What's the molarity of the concentrated solution? 74.28 gram sample of barium hydroxide. 74, let's see, this is 17. 0.28 gram sample of barium hydroxide. Barium is 2+, so we need 2 of these. And we need to convert that into moles. Right? So barium is a big atom. 13733. 2 oxygens. Right? 2 oxygens and 2 hydrogens. 5, 3, 11, carry the 1, 7, 1. 171.35. This will give us the number of moles of barium hydroxide. Zero 0.433 moles. Okay. So, and we're dissolving it in enough water to make 2.45 liters. So the concentrated molarity of the solution is 0.433 moles divided by 2.450 liters. Which is 0.177 molarity. That's the concentrated concentration of the molarity of the concentration. Starting to sound like Joe Biden. How many milliliters of this solution? How many milliliters of this solution must be diluted with water in order to make 1 liter of a 0.1 molar? So if this is the concentrated, we need to know how much of that do we need to take out and dilute to 1 liter. I think there are 3 of them to make 0.1 molar. Okay, so you remember the relationship? Concentrated yields diluted. Right? Or M1V1 equals M2V2. That's your dilution formula. MC, concentrated molarity, volume that you take out of that concentrated molarity and dilute it to this volume to give you that molarity. Yeah, BD, dilute, concentrated. Right? So if we want to solve for this one, it's dilute over dilute divided by concentrated. So this is 0.100 molar, and this is 1.00 liters, and this is 0.177 molar. And that should give us the volume in liters. 0.1 divided by 0.177 is 0.565 liters, but the answers are in milliliters. So the unit gets smaller, number has to get bigger. So 1,000 times is milliliters. 1, 2, 3. 565 milliliters of this solution diluted to 1 liter gives us that concentration. So A is the answer.
Wait.
Okay. You got this stuff?
You do.
I want to see if there are any squirrely ones in here. 18 is a dilution problem also, and the answer to that one's A. Can we skip that one? I want to find one that may take some explaining. How about these types of chemical reactions? Are you comfortable with those? Okay, 28. Let's do that one. The following reactions, and there are those two, are examples of what type of reaction? Well, your choices are oxidation reduction, acid base, precipitation. Oxidation reduction. In order to be oxidation reduction, the oxidation states of the elements have to change in the process, right? And if you check the oxidation states for zinc, it's the same on both sides. For bromine, same on both sides. Silver, same. Nitrate, same. Nitrogen, same. Oxygen, same, because nitrate stayed the same the whole way. And similarly, the one below it is not a redox reaction. Neither one of those are redox reactions. You know, you check the oxidation states and you find that they're not. They're not acid-base reactions either, right? You don't have any H's in there with OH's. So the only option we have is precipitation. And so you look at aqueous solution here plus aqueous solution there yields aqueous here and a solid. That's a key to precipitation reactions. You put two solutions. Well, yeah, in practical terms, but you put two solutions together and you get a solid. That's a precipitation reaction. Same for the bottom one. Silver bromide forms a solid out of two solutions. Oh, so the answer is C, precipitation. 29. So we have oxidation, reduction, combustion, precipitation. In order to be a combustion, you have to react something with pure oxygen. Only one of them satisfies that, right? Not all. So we can't use that one. Precipitation. We don't have any aqueous being replaced by solids, right? So that one doesn't work. So the only one that makes any sense is oxidation reduction, and a rule of thumb shows you that it is, right? Remember what I said, if you have an element on one side with reacting with anything, and it ends up in a compound on the other side, that is an oxidation reduction, right? Because this is zero, and when it goes into a compound, it has to assume a different oxidation state. So, and that's what we have. Aluminum and bromine make aluminum bromide, right? Two elements make a compound. That's oxidation reduction. Silver oxide decomposes into silver and oxygen. That's oxidation reduction. And all combustion reactions are oxidation reduction. So all three of those are redox reactions. It's just A. I know, but the 29 says all of the following reactions can be classified as. Right. Only the third one is a combustion. So all of them can't be classified that way, but all of them can be classified as redox. Tricky wording. Which of the following salts is insoluble in water? So if you want to find that one out, what you need is that solubility chart on your review document. Yeah, it's on the very last page with the grayed out squares on it. All you have to do is take the cation, find it across the top, right, and then follow it down until you meet the row that has your anion in it, and see what's that square, right? Sodium sulfide. All right, sodium's the first one. Down to sulfide, it's clear. Potassium carbonate. So we find potassium, there it is. Go down to carbonate, it's clear, soluble. Lead nitrate. So we go all the way over to the right. Lead's next to the last one, top. Go down to nitrate. Oh, it's the first one. It's soluble. Calcium chloride. All right, find calcium, go down to chloride, and it's soluble. All of them are soluble. Okay, trick question. We do that instead of making you memorize all the rules. Since you're not going to be chemists, then I don't see any problem with that. Let's see, 37. Consider an aqueous solution of calcium nitrate added to an aqueous solution of sodium phosphate. What's the formula of the solid form? So if you got an aqueous solution of calcium nitrate, this is 37. How's our time? Oh, I'm past time. Okay, so let me give you the answers. 37 is C. 38 is B. 39 is C. 38, right, is B. 39 is C. 40 is A. Let's see. So 38, 39, and 40 are based upon this thing up here where you react barium chloride and silver nitrate. You have to write out the molecular equation, balance it, then write out the complete ionic equation from that. And then you have to cross out the spectators and see what's left over. And in this case, you have left over is coefficients in front of all the terms are 2, 2, and 2. You have to reduce it further. That's why the last one, the answer is A, silver ions. Once you cross out the spectators, you're going to have 2 silvers, the ones that don't participate in the precipitation, the ones that stay in solution on both sides. Do we need to work that?
The one that can't stand is 30, not.
Yeah, they stay in solution. Yeah. In these types of reactions, precipitation reactions, the only interesting players are the ones that participate in the precipitation. Right. So in this case, it's let's see, silver and chloride. Those are the active participants because silver, once silver combines with chloride, it precipitates. Barium and nitrate stay in solution on both sides of the reaction. Right, so you cross them out. Those are spectators. Okay. Let's see, who's next? 45 is E. Let's see, next one is 50. 50 is C. For 50, you need to write the balanced acid-base reaction for sulfuric acid and sodium hydroxide. Right, produces sodium sulfate salt plus water. Balance it, and then once you've determined how many moles of acid are reactant, then you can convert that into sodium hydroxide by our usual stoichiometry ratios. You know, the coefficients. 25 milliliters times 2.7 molar will give you how many moles of acid. Right. Then you convert that to how many moles of base, and then convert it back to mass. But you need the balanced equation. It's an acid-base reaction. All right. Oxidation states, 52 is B. 53 is D. D as in dog. Let's see. Alpha, Bravo, Charlie, Delta. D is Delta. 55 is Delta. Let's get military. 56 is Charlie. Please? Yeah, I think so. 57 is Bravo. 61 is, uh-oh, what comes after delta? Echo, right? Yeah. E is, echo is 61. Uh-huh. 63 is, delta, as in delta force.
63.
Uh-huh, is delta. 66 is, alpha. Is that right? Alpha. 68 is, Bravo. It used to be Abel Baker, A and B, but then they changed it. Huh? That's military, yeah. Let's see, 68 is Bravo. 69 is, Alpha. 71 is Delta. Uh-huh. 71's Delta. And let's see, I didn't do any of those. I think that's it. Yep, that's it. If you can answer the ones we've done so far and those, then you should be able to handle those. And this useful information will be in the test document. So they have that page, it'll have the polyatomic ions there. It'll have the periodic table, and it'll have this solubility chart, just like your review document. Okay. Stop the share and end the Zoom. Okay.